All right. Welcome back. And our second speaker is Yevgeny Liokumovich, and from University of Toronto. His talk is on Weyl law for the volume spectra. Let's welcome.
Thank you very much for the introduction, and thank you very much to the organizers for this conference. It's amazing to be here. All of the talks are extremely interesting, enlightening, and impressive. I'm going to talk about my joint work with Fernando Marques, Andre Neves, and some related works. When I give slides talks, I go through slides too fast, and it's hard to understand. And when I give Blackboard talks, I go too slow, and I can't get to the interesting part. So I'm going to try a combination today of slides and talks. So it will be hard to understand that we won't get to the interesting part. I'm going to start with a very general setting to illustrate a key idea. So say we have some compact manifold. It could be a sphere or maybe a disk in R2. And we will look at some space of functions from our manifold, maybe space of L2 functions, or if you like, a smaller space, polynomials on the disk. And we will consider a functional which is homogeneous. So if you multiply your function by some non-zero number, the value of the functional doesn't change. And so what's nice about this functional is that you can projectivize this Hilbert space now and just consider your functional as acting on the projective space, on the space of lines. Right? So the value of the functional only depends on which line are you on. And so you can think about this functional now as a map from this infinite projective space into R. And what's really nice about homogeneous maps like that is that when you think of them as maps from the infinite projective space, you now suddenly have a lot of topology, and very nice topology, right? Because if you consider homology or cohomology of RP infinity with Z2 coefficients, then you have exactly one non-trivial element in homology or cohomology in each dimension. You have 1 and 2 and 0 and 1 and 2 and 3. Okay? And so these non-trivial homology and cohomology elements can help us find critical points of our function. So if you want to do analysis on this map and you want to find critical points of this functional, then you can now you can now do the following here. You can pick this unique non-trivial element of your homology or cohomology, and we will do the cohomology, and you'll see later why it's so nice to do cohomology. And you can consider the non-trivial map that detects this cohomology class, and you can define the following minimax quantity. You consider all of these non-trivial maps from RPK into RP infinity, and you try to make the maximum as small as possible. You push it down. And so the intuition that you have is that as you push it down, it's going to get stuck somewhere because of the topology. And as it gets stuck at some point where you cannot push it down any longer, we asked about this point. What is the gradient of E at that point? And if the gradient is non-zero, then you can do the gradient flow and push it even further. But you can't push it even further because that's the minimax value by definition. And so what that tells you is that what this intuition tells you is that you hope to find a critical point that way. So this will be the point where the gradient is zero, and this will be your critical value. So the topology helps us find critical values of our functional. Okay. So let's consider some examples. So a classical example is that in a somewhat strange and maybe not intuitive way, what you just described is eigenvalues of the Laplacian. Right? If your energy is the Rayleigh quotient, then this is the famous min-max characterization of the eigenvalues of Laplacian. And well, in this case, these RPK maps are just linear maps. And so it may seem like we're doing, working too hard to do something simple. But this setup applies to many things. For example, you can look at not a linear spectrum of a linear operator of Laplacian, but you can look at the P-Laplacian and do the same thing. And then you'll be able to find eigenvalues of the P-Laplacian. Right? Again, it's going to be a homogeneous map on your space of functions. In this case, the Sobolev space W1P, and these values will turn out to be eigenvalues of the P-Laplacian. It turns out that linear maps are the minimizers. So it's in this case, it will be just it will just get the linear maps. Exactly. Right. So for the Laplacian, you'll just get the linear ones, but in general, you don't. And so this is a way of generalizing this Rayleigh quotient characterization of eigenvalues of Laplacian to more general settings. Mm-hmm. They will be eigenvalues. They may not be all of them. Right? So you'll get some eigenvalues of, you will get eigenvalues of the P-Laplacian that way. It's not clear if you get all of the eigenvalues of the Laplacian. That's right. Yeah, so that it shouldn't be the case. It should be some sequence of eigenvalues. That's right. Sorry. But in the sense, yeah. Thank you. But what we're going to be interested in today is a somewhat unusual functional, just the volume functional. Yeah, so you can look at your map, you look at the zero set. If it happens to be nice and measurable, then you can compute its main n-1 Hausdorff measure, and that's going to be another homogeneous functional on your space of functions. Mm-hmm. Yes. Exactly. Yeah, we'll get there in a moment. Exactly. That's yeah, we'll get there in a moment. Right. So we will be interested in doing working on variational problems and finding critical points of the volume function. Okay. So so how does this point of view help us? The insight is that the fact that we're working on cohomology, exactly an idea going back to Lusternik and Schnirelmann, helps us to prove interesting inequalities about this. Yes. Well, if you multiply the function by a constant, the volume of the zero doesn't change. The zero, the volume of the. Okay. So we can prove the following interesting inequality, which allows us to relate. So this is our M, and then we have some sets U1 and U2 in here. So we can relate the, okay, so if we have an inequality like that, so I didn't get to what we want to prove exactly. So we'll relate the, this element of the spectrum of the whole space to elements of the spectrum of subsets. So assume that our energy satisfies this inequality. In particular, this is true about the volume, right? So if you have some nodal set, then of course the volume of the whole thing is larger than the volumes of the restrictions to these two subsets. Yeah. So if you have this relationship for your energy, then immediately you get this beautiful inequality. And how can you prove that? Well, you prove that using the following fact from topology, which goes back to Sternik and Schnittelman, and you usually read it, in the beginning of a textbook on the Sternik-Schnittelman category. And the observation, which now we can just prove from Myers-Vitori's long exact sequence, that if you have two cohomology elements and one of them vanishes on one subset of your space and another vanishes on another subset of the space, then the cup product will vanish on the union. That's a topological fact. And so now we can use this fact to prove this inequality. So we can define two subsets of P of our space of functions. So the first one will be all of those functions that, so that the energy of the restriction of F to U1 will be smaller than W1 of U1. And V2 will be for the energy of restriction to U2 will be less than W1 of U2. So these are going to be our two sets. And so suppose we have a map, and this map has values smaller than the sum of W1 of U1 and W1 of U2. And we would like to say that such a map cannot detect the second cohomology class, which means that the W2 of M has to be larger than that. W2 of the union has to be larger than the sum. Well, so the fact that, so if you have that the, if you have that the restriction of F to U1 has energy less than W on U1, then it's going to be in V1. And if it's the restriction to U2, then it's going to be in V2, right? So if now the energy is less than the sum, it has to be in either V1 or V2, right? Because if it was in neither, then it would have, mass larger. Okay. So then that tells us that if you look at the second non-trivial class in the cohomology of the space, C2 coefficients, well, that is just the cup power of cup product of the first class and the first class, because we're working with RP infinity. And so therefore, the pullback of this cohomology class is the same thing as the pullback of the product. We're using the cohomology structure of RP infinity, and that will have to be 0 because alpha 1 vanishes on V1 and V2. So this way, we proved that if your map from RP2 satisfies this inequality, then it cannot detect the second non-trivial class. And so when you do the minimax over all things that detect this class, it has to be larger than this sum. So it's a very simple idea, but it allows you to relate the elements of your spectrum corresponding to the union to the spectrum of the subsets. And if you add to that, for example, you're looking at something like a cube, now you can put smaller copies of your cube inside, right? And you can apply similar inequalities where here you have P plus Q, and here you have P, and here you have Q, and inside you have, scaled copies of the object that you're working with. And you can derive all sorts of very nice inequalities about this spectrum with very few assumptions. So it's a very sort of very few ingredients that give you quite a lot of results. Okay, so that was any questions? So that was sort of a general setup to illustrate the idea. Now we will be interested in the variational theory of the volume functional. And in codimension one, you can actually develop a theory for zero sets of functions and obtain critical points of the volume functional this way. But if you go into higher codimension, then it becomes quite difficult. And so a somewhat more flexible and nicer setup is to work with a space of flat cycles. So this was developed in the 20th century in geometric measure theory, specifically to work with variational problems on objects of different dimensions and codimensions and different topology. And so let me quickly say what these are. So you're just looking at cycles in the same way as in the definition of singular homology, except that you ask the maps to be Lipschitz, and you can define a notion of distance, well, sort of semi-distance, pseudo-distance between them. If you have one cycle and another cycle, then you consider them to be close to each other if there is a m+1 dimensional chain whose boundary is the difference between these two cycles. And if you can find a chain whose volume is small, then these two cycles are close to each other. And so what you do is you look at the space of such Lipschitz cycles. You mod out by the equivalence relation that if two cycles have zero flat distance between them, you consider them to be the same thing. Right? So in particular, if you have two cycles that are parameterized in a different way, then they're the same thing. If you have a cycle and plus you add some spikes which don't bound anything, then that's the same thing. Right? So you consider these equivalence classes of objects, and you take the completion, and that's your space of flat cycles. So somehow it's a very flexible, large space, which allows you to do a lot of things. Okay, and so this space has been successfully used in geometric measure theory to solve variational problems. If you have a non-trivial codimension one homology class and you minimize in that class in the space of flat cycles, then you will obtain a smooth embedded minimal hypersurface. And in other dimensions and codimensions, you will also obtain some objects, but they may have singularities. Okay. So this space is, from the point of view of geometric measure theory, especially in higher codimension, is appears to be the right one to work with if you want to develop this variational theory. And in codimension one, it has exactly the same topology as we wanted, as we worked with previously. Mod 2 cycles in codimension one are weakly homotopy equivalent to RP infinity. But more generally, they may not be homotopy equivalent to RP infinity, but they have still this property that you have a fundamental class such that all of the cup powers of this fundamental class will be non-zero. And so this allows you to define these families of K-sweep outs, what we call them, these non-trivial families that we will use to define nonlinear spectrum. So let me maybe pause here for a second. What time should I finish? Okay, that's good. So let me maybe give you an example, because to make it a bit less abstract. So let's say our manifold is a unit disk, and consider the projection map onto -1, 1. And let pk to be a space of polynomials of one variable of degree less or equal than k. And we projectivize that. So the space of up to multiplication by a constant. So that's just our pk. Okay. And so consider the following family. Consider a map from pk into the space of one cycles on G2 with Z2 coefficients, which takes a polynomial and sends it to zeros of p counted with mod 2 multiplicity. Sorry, with multiplicity counted modulo 2. Okay. Right. So now we have this map phi. So that's pk of p pk, and that will be a k sweep out. So for k equals 1, it's going to look like as just, sorry, what I want to do is I want to do pi inverse of that. So for 1, we'll just have, just linear functions, they have zeros anywhere between, just one 0 anywhere between -1 and 1. So your one sweep out will be the pre-image by the projection, and it will look like a line moving from left to right. And for two sweep outs, you have two lines moving independently. Sometimes they will meet each other and cancel each other out, kill each other. And for three sweep out, you'll have three lines that will be sometimes meeting with each other, and then we will count them mod 2. So that's going to be a three sweep out. So this is what a k sweep out looks like in this setting. Any questions? All right. So then what we can do is we can define this min-max quantity. We look at the supremum of, I forgot to put volume here, the k volume. That's going to be supremum of m volume. So we're looking at supremum of volume m of phi of x, and we minimize over all maps into the space of m cycles such that the pullback of lambda to the k is non-zero. So in the same way as we did before, but now somewhat different, slightly different space. And we hope that this way we detect critical points of the volume functional, which are known as minimal submanifolds. And indeed, that's something that was proved by Almgren in the 60s, that each of these values will correspond to volumes of some combination of m-dimensional minimal submanifolds, but in general, they can be quite singular. And in two instances, we have better regularity. One instance is dimension 1. When we're looking at one cycles in the space, then we know that these values will be equal to sums of length of stationary geodesic nets. And I'll explain what they are in a moment. Just right now, just think about them as a slight generalization of closed geodesic. And these ni's are integers. We take them to be positive integers. And in codimension 1, when the dimension between 3 and 7 fits, building on curvature estimates of Shane-Timon Yao and Shane-Timon, proved that these are actually going to be a linear combination with integer coefficients of volumes of embedded smooth minimal hypersurfaces. And then in high dimensions, they may have singularities, but they will have codimensionate. So these are the two setups. And at first you may think, wow, that's amazing. We now obtain infinitely many critical points of the volume functional. And this is related to Yau's conjecture from the 80s that every closed tree manifold contains infinitely many distinct embedded minimal surfaces. More. But the issue here is that they don't need to be distinct, right? In principle, they could be just a multiple of one single minimal hypersurface. So it gives you one, yes, but maybe just one. Right? Maybe you have multiplicity and you get the same thing again and again. So all this result gives you one stationary geodesic net and one smooth minimal hypersurface. Okay. So what are stationary geodesic nets? They're critical points of maps from graphs, one-dimensional graphs with vertices and edges into your manifold. And what this is equivalent to is that inside the manifold, it looks like geodesic arcs connected at vertices, and at each vertex, the outward pointing tangent vectors sum up to 0. So for example, on S2, the 3 half-great circles with 120-degree angles would be an example of a stationary geodesic. That sort of natural object that you obtain by from variational problems on the space of one cycles. Okay, so it turns out that in order to solve Yau's conjecture, one needs to yes, because that's a good question, because you can show that this value is greater than 0. If you didn't know that, then it would give you nothing. That's right. It gives you a proof of existence of a stationary geodesic net without thinking about the topology of the space, but you have to think about the topology of the space of cycles, which was proved by Almgren. Yes. And in dimension 2, it turns out that there will actually be geodesics. So we'll get to that. I guess existence of a closed geodesic on surfaces is maybe more of a classical result. Yeah. Okay. So now the key idea is to look more carefully on the values of these quantities. And so initially, Almgren showed that for the fundamental class, for the fundamental slip out, the smallest one, on the round sphere, you get precisely the volume of the geodesic sphere of that dimension. So that was quite a spectacular result. But if you look at the higher parameter families, then there is a result in a paper of Gromov, which kind of initiated this whole point of view that I talked about in the beginning. But it's a paper from 1988, which is maybe wasn't very well read, and later Guth reproved and generalized some of these results in a more readable way. And it tells you that up to a constant, it has an interesting sublinear growth for the sphere. So as you look at higher and higher parameter families, then they will grow like k to the power n minus m over n. So for hypersurfaces, that will be like k to the power 1 over n. And it's a striking contrast to the picture I drew here, right? So for the disk, what you see here is that as you increase the number of parameters, the maximum goes linearly as k. But in fact, you can deform this family in such a way that the maximal length is only square root of k. And the key is to get these lines to cancel each other enough, because there are Z2 cycles. And then we have this beautiful theory, results by Yao with Peter Lee and Paul Young and Hirsch, and results of Hirsch and Koribar, that bound eigenvalues of the Laplacian in various geometric settings. So for example, for surfaces, we have bounds in terms of the genus and the area. If you have reach a greater or equal than 0, then you have this just result in terms of the volume. And there's a generalization, interesting generalization of that due to Asma Hassanijad. If you know that your metric is conformally equivalent to to a manifold with reaching greater or equal than -1, then you can obtain this nice balance. So this, in some sense, this slightly weird invariant for surfaces is just the genus times 2 pi. And so this is kind of a generalization of that. And then for each of these results, we have an analogous result for this nonlinear spectrum for width. So for surfaces, we have a result that was for 1 cycles, for 1 sleep-outs, was proven by Balashov and Sabaru, and I generalized it to K. And then in this case, in that case, we have similar results. So, so this, kind of final result, which combines these two, was proved for K equals 1 by myself and Parker Glinady, and Richard Wang, when he was visiting Toronto, proved the full conjecture. And that kind of, suggests that there's something fundamentally important about this somewhat, interesting connection between linear and nonlinear spectrum. And that led Gromov to conjecture that this nonlinear width should also satisfy the Weyl law. Right? So for the eigenvalues of Laplacian, we know that asymptotically, they don't depend on any features of the geometry except for the volume. And Gromov conjectured that the same will be true for this nonlinear spectrum. And so the current status of this result is that we proved it with Fernando and Andre in 2016 for families of codimension 1 cycles for hypersurfaces. We also proved it for all M for domains in Rn. Then with Larry Guth, we proved the case of 1 cycles in 3 manifolds. And recently, my student Bruno Staffa proved it for 1 cycles and all dimensions. Yes? Right, so it's quite difficult, but this specific case, S2, was solved by Otis Chodos and Christos Mantolidis not a few years ago, and they explicitly computed the spectrum, and that's the only case where we know the spectrum on round S2. So we know it on round S2, and we don't know it on the flat disk, for example. We don't know, and it's a very, very yeah, and it's quite difficult. For example, the solution of the Wilmore conjecture by Marcus and Nevis was, the key step is to compute the 5 width of S3, the fifth element, That is sort of the yeah, so it's quite difficult. We could understand, and we don't know this constant in any dimensions except for n equals 2. M equals 1, and the reason we know it is because Chodos and Mantolidis computed the spectrum for us too. That's why we know this constant. Otherwise, we don't know this constant for any other values. No, right. So yes, he just was based on the analogy, and basically his motivation was what I showed in the beginning. This if you start, looking at this inequality that you get from cohomology, and scaling things and putting them inside itself, then that's the sort of thing that you get. That's the constants that you get here, right? So you get this constant here. You get this power n minus m over n. And so basically, his motivation was that he. So I'm going right way. No, I'm going the wrong way. So his motivation was using this trick. He computed the lower and the upper bounds, and then hoped that maybe they meet in the same way as they meet for eigenvalues of Laplacian. Okay. Mm-hmm. Not known what's on the torus. So it turns out to be that the polynomial is the most efficient thing on the sphere. If you look at the 0 sets of homogeneous polynomials on R3 intersection with S2, so that will be the optimal thing. If you look at 0 sets of polynomials on the disk, it will not be the optimal thing. the asymptotically you can see. If you try the most obvious thing on the torus, it's not the optimal thing. It's actually tricky to even come up with a conjecture of what it is on the square torus. When do I finish? 20 minutes. Okay, wonderful. So I'm probably a bit more on the too fast than probably both. Okay, so let me talk a little bit about applications. So we mentioned this conjecture of Yao about existence of infinitely many minimal hypersurfaces. And it turns out that understanding, the careful understanding of the asymptotics of this width gives you this conjecture in the generic case. In fact, it gives you more. For a generic metric, you know that for any open set, there will be some minimal hypersurface that passes through, or some stationary geodesic net that passes through. So you can go from the Weyl law to the result that for a generic set of metrics in the Bayer sense, for C infinity or Ck, the set of smooth embedded minimal hypersurface in dimensions between 3 and 7 is dense in your metric. So in the manifold. Or, so in which space the minimal hypersurfaces are dense? So the statement is like this. So yeah, so look at the space of metrics, and inside you have this countable intersection of open and dense sets. So maybe so these are C infinity metrics, or it's also true for CK metrics, such that for all G in the space, you have that, and for all open U inside G, there exists some smooth embedded minimal hypersurface sigma, such that the intersection of sigma with U is not empty. Okay. So any open set, you will have some minimal hypersurface. It's smooth, embedded, compact, so necessarily you have infinitely many objects like that. And with my student Bruno stuff, we proved the analogous result for stationary geodesic nets, and in dimension 2 for closed geodesics. And the reason we can do the two-dimensional case is this paper of Chodosh and Montolidis that I mentioned, which allowed them, to conclude that the stationary geodesic nets are actually going to be closed geodesics by combining sort of two min-max approaches. Really nice paper. I love it. Okay. So let me quickly sketch the idea of the proof, because I think it's really nice. The first observation is that the set of embedded minimal submanifolds for a generic metric is countable. This follows from the bumpy metrics theorem of Brian White for minimal submanifolds, and Bruno proved it. He developed a sort of analogous theory for stationary geodesic nets. Okay, so now we're going to do the following. We will start with manifold M, and we pick some small open set, let's say ball B, around some point. And we will define a small bump function, T, and we will consider a family of metrics GT, which is the original metric, plus T times this bump function. And so as T increases, the volume of the manifold will increase. And by the Weyl law, it means that the asymptotics will change, right? So if you now look at this map, so if you now look at the map, the kth width of GT, right? So what does this map do? So we take that. So now it takes t and it sends it to wk gt, right? So that's going to be a map from 0, 1 to this interval wk of g0 to wk of g1. Now, suppose there are no minimal hypersurfaces passing through this small ball, and when you perturb the metric, there is still no minimal hypersurfaces passing through the small ball. So what does that mean? That means that as we change this metric, all of the minimal hypersurfaces will be outside. So there will be the same minimal hypersurfaces as in the original metric. So we're changing the metric, but we are not changing the minimal hypersurfaces because in the neighborhood, nothing passes through this ball. That means that this map is sending the interval 0, 1 into here, but all of the values of this map are contained inside linear combinations of volumes of a countable set of things. So the image of this map is countable, and yet it's going to be surjective onto this interval of non-zero length. So we will have that this entire interval will have to be contained in some countable collection of linear combinations of volumes of minimal hypersurfaces, which is a countable. And so we get a contradiction. So that tells you that I can take any open set and I can take a small perturbation of the metric, and there will have to be minimal hypersurface passing. So that's okay. Yeah. That's the range in which we have regularity. But the Weyl law we have for all dimensions. So in dimensions larger than that, these minimal hypersurfaces will have codimensionate singularities. And in that case, we just don't have this result. We don't have the countableness. That's all that's missing. The Weyl law is there. We just don't have. Surprisingly, it's hard to get. Right. Surprisingly, it's hard to get. Yeah. So for stationary geodesic net, there's quite a bit of work that Bruno had to do to develop this theory. Yes. Surprisingly, it's hard to get. That you would like to say that the volumes of stationary integral variables, is a set of measure zero. We'd like to have Sard's lemma of that kind, but we don't know how to prove that. Okay. In fact, one can prove more. One can prove an equidistribution result, which means that you have a sequence of minimal surfaces or stationary geodesic nets which fill up your manifold in a way proportional, in a sort of equal way. Yeah? So the amount of volume that you have in the set is also the amount of length of volume that you have of these minimal submanifolds or stationary geodesic nets filling it up. And it's quite a surprising result that we have this for a generic set of metrics. Like there are many cool results like that in dynamical systems for hyperbolic manifolds or negatively curved manifolds. But it's kind of surprising to get a result like that for generic arbitrary metric without curvature assumptions. And the idea to prove this result is to differentiate the Weyl law. So when you take the derivative on the left side, then here what will come out is the derivative of volumes of minimal hypersurfaces as you vary the metric. And what you get on the right side is the derivative of the volume of the manifold. So if you look at perturbations, various perturbations of your metric and small balls, then the amount you change the volume should is related now to the amount you change the volume of the minimal hypersurface or stationary geodesic nets inside that. but then, of course, it's it's quite actually technical to prove this result. But the main idea is just take the derivative, and I think this is. Thank you.
Okay, so any questions or comments?
Thank you for your talk. What's the main ingredient in the proof of the Weyl law? Is it the lemma you mentioned at the beginning?
That's right. So that's a key ingredient in the proof of the Weyl law. Carefully. So in Rn, what you can do is you can tile an open set with scaled copies of this set, and use that lemma to compare this spectrum, which is is somehow similar to how the Weyl originally proved his Weyl law. So I'm going to.
The classical Weyl law is proved via the heat kernel.
Yes, but I think even before that, I think there were some ideas of this time before the heat. But right. But for a manifold, there's an issue that you can take a compact manifold, scale it, and put it inside itself. And so what we do is we cut manifold into pieces. We paste them besides each other. And then we can construct almost optimal families of cycles in each region. And then we want to, so I'm not saying it right. And so to say it right would be something like that. So if you have a manifold M, we cut it into pieces. We put these pieces in Rn. Now we have a bunch of pieces in Rn. And we can even connect them, if you like. Now, they're not in the order that they were in the original manifold. Now, we have a subset of Rn, and we can now sweep it out in an optimal way. Okay? And now we put it back. But as we put it back, of course, it's now not a cycle at all. It's a really weird thing with, with chains, with pieces all, with boundary everywhere. But what you'd like to do is you'd like to connect it back into a family of cycles. And to connect it back, you need to add a bunch of chains which live in the boundaries of these regions. But the boundaries of these regions, they're fixed, and k goes to infinity. And because we are dealing with mod 2 cycles, the worst amount of stuff that we need to add is just the total area of all of the boundaries of these regions. And that's constant, and k goes to infinity. So if we are able to add them in a way that produces a k sweep out, then we are good. But this becomes difficult in higher codimension, because in higher codimension, you don't have something like that. You have something that looks like. Yeah. And so then if you have a family of relative cycles living in one box and a family of relative cycles in another box, and you need to somehow connect them to each other in a way that controls the mass, the volume of the thing that you put in, then that becomes a tricky problem. And that's why the higher codimension case, we only have it for one cycles for now.
More questions?
This conjecture of Yao that you mentioned, but
it was proved by Antoine Song for all metrics, not just generic metrics. I wanted to mention that. And the proof also uses Weyl law, but a slightly different one. So he has it uses actually both Weyl laws, but he also had another Weyl law. It's a quite ingenious idea. So he cuts manifold into what he calls a sort of a core region. So this is where any minimal hypersurface will intersect any other minimal hypersurface. And then he adds infinite cylinders to that. And he proves a Weyl law, which is a linear Weyl law for this strange object. And then she's able to prove infinitely many minimal hypersurfaces for all that. It's quite a delicate argument. Thanks.
More questions? Okay, so if there is no further question, let's thank Professor Liokumovich again.